see. Oh no, now I'm gonna get some comments. Oh no. So you just form the sum, n equals 1 to infinity, of e to the minus n squared pi squared t over L squared sine of n pi x over L. So this is sort of our template solution, right? Now you need to fit u of what? U of x comma 0 equals to f of x, right? To that. So what happens if you put t equals to 0 into this? The exponential goes away, right? And you know what? I forgot something important. We should say like a sub n here. We need some numbers, some weights. So a sub n sine of n pi x over L. This is u of x comma 0, right? Now how do you match your template solution to the initial condition? What you want to do is you want to take the given initial temperature distribution and sort of break it into its fundamental frequencies in some sense. I mean, you just rewrite f of x as equal to a sum over, let's say, b sub n sine of n pi x over L, n equals 1 to infinity, where b sub n is equal to the 2 over L, the integral from 0 to L, sine of n pi x over L, f of x dx. Now, the derivation of this formula for the b sub n, the derivation of the formula there for that b sub n has to do with a calculation similar to the one I did after break today. This is derived in the second section on Fourier series. In this series, this we're looking at is a so-called Fourier sine series. Well, this is a Fourier sine series, and the fact of the matter is separation of variables naturally led us to see that the solution to the heat equation is a Fourier sine series. And then, well, how do you actually, so what should we choose a sub n to be? There's not much thinking here. If we want to make this match that, we simply make the coefficients match, right? We just make this and that be the same. These are not the same a's and b's I was doing it right after break, okay? I just use different letter to disconnect them. Like maybe I should make this Pac-Man and make this ghost. Sorry, that was starting to be something I was seeing in that road rage thing I watched the other day. So ghost. And the point is that these coefficients, if you force them to match, then that means that choosing the Pac-Mans to be these specific numbers will force us to fit the initial condition with our template solution. And this is how we solve PDEs. It's like the same thing for the wave equation and for Laplace's equation. We form a product solution, plug it into the differential equation, and then face the boundary values that will give us, sort of either sines or cosines typically, or some sum of those. And then we use Fourier analysis to fit the initial conditions, or sometimes the boundary conditions, to that template solution. That's basically the idea. There's a lot to it, right? I mean, a lot of moving pieces here, but nothing you really haven't done before except the Fourier thing, right? That's new, but it's also pretty straightforward. It's really not so different than Taylor series. It's just Taylor series are nicer, right? If you want to find the coefficient in the Taylor series, what do? Take your function, differentiate as many times as you like, plug in the number, coefficient found, right? To find Fourier series, you have to do integrations of your given function times sines or cosines with the appropriate arguments. But this is not an in-class part of the test. This is take-home, and you are allowed to use Wolfram Alpha, Mathematica, whatever you want to do the integrations, right? Just do them correctly. anyway, I have some actual initial conditions and worked out problems we can look at when we meet again. Actually, when we meet again, we'll have class interaction, right? No? You guys say you're for classroom interaction, but when we actually do it, so often, not appreciated. Yes, good.